Hello, I'm Tom Tracy, a postdoc researcher from the University of Virginia, and I will be presenting our work on FPGA-based runtime verification. The other authors of our paper are Kevin Skadron, also from UVA, and our collaborators from Rice University, Lucas Tabajara and his advisor Moshe Varti. Runtime verification evaluates a system at runtime against a set of formal specifications that encode the system's intended runtime behavior. It is particularly useful for safety-critical and autonomous systems where it can be used to discover erroneous behavior at runtime and allow for graceful recovery. Runtime verification engines that verify a system are called runtime monitors. These monitors are generated before runtime as part of a preprocessing step from a set of formal specifications, as shown by the dotted line. At runtime, these runtime monitors monitor the system signals. If the system trace of signals results in a violation of the formal specifications from which the monitor was generated, the monitor will alert the system for recovery or notification. Formal specifications are represented by a formal specification language, of which there are many. One contemporary and commonplace temporal specification language is LTLf, or Linear Temporal Logic over Finite Traces. This is a formal language that includes temporal primitives, and a formal specification is a formula over a set of system signals that includes these temporal primitives. LTLf uses the same syntax as LTL, but interprets the system signals over a finite trace instead of an infinite one. This makes LTLf a natural choice for runtime verification because we are trying to detect violations in a finite amount of time. Previous work has shown that LTLf formulas can be converted into finite state automata, of which we will consider NFAs, or non-deterministic finite state automata, or DFAs, deterministic finite state automata, where these finite state automata recognize inputs that correspond to matching the formulas from which they were generated. Temporal formulas can be converted into NFAs or DFAs before runtime, and below are two examples of DFAs generated from two different LTLf formulas. The first is an automaton that recognizes an input such that signal P must be active up until signal Q. The second is an automaton that recognizes an input such that if there is an active P signal, there must be an active Q signal after that P signal. Previous work, including Grapefruit, published earlier this year at FCCM, has shown that FPGAs significantly outperform CPUs for automata processing, especially as the number of automata, or in our case LTLf formulas, increases. FPGAs, or field programmable gate arrays, are integrated circuits that function as programmable digital circuits. They implement these circuits by configuring and connecting logic blocks in a large two-dimensional array. Each configurable logic block, or CLB, contains several hardware elements, including lookup tables that implement digital logic gates, flip-flops that store state, and multiplexers that control the flow of data. These CLBs are then connected by way of a large configurable routing matrix. Previous FPGA accelerated automata work, including Grapefruit, has used an explicit automata encoding to represent the individual automata in hardware on the FPGA. With this approach, every state in the automaton is mapped to its own hardware resources, and this allows for multiple states to transition and be active at the same time. This approach requires more hardware, but transitions are fast because they can be done concurrently and are conveyed via wires. An alternative approach uses symbolic automata. With this approach, states are encoded with bit vectors, but transitions are represented with combinational logic. The diagrams on the right show the two different architectures used for automata processing on FPGAs. The top right explicit representation encodes the automaton shown on the left with hardware, where the state colors indicate state-specific hardware. The bottom right shows how symbolic automata are represented with lookup tables. We utilize Grapefruit for explicit automata and extend it to include symbolic automata functionality. In addition to choosing between explicit and symbolic automata representations, automata can be represented as non-deterministic finite state automata, or NFAs, as well as deterministic finite state automata, or DFAs. An NFA is a finite state automaton where the computation of the automaton can result in multiple concurrent transitions and states. The limitations within NFAs are that minimizing NFAs to a minimum state size is an exponential time algorithm requiring heuristics for larger NFAs. A symbolic representation of NFAs comes with a state bit vector that must be linear in state count, as multiple states can be active at a given time. A DFA is a finite state automaton where only a single state can be active at a given time. Minimizing DFAs can be done with a much faster polynomial time algorithm, but converting NFAs to DFAs can come with a worst-case exponential state blowup, making some NFA to DFA transformations resource prohibitive on FPGAs. DFA state bit vectors can also be represented with a logarithmic number of bits, unlike linearly on NFAs, because only a single state can be active at a given time with DFAs. These differing DFA architectures, either explicit with hardware dedicated to each state, or symbolic with truth tables that represent state transitions, as well as trade-offs between DFAs and NFAs, where DFAs can be minimized for cheaper and require fewer bits in their state representation, while NFAs can have worst-case exponentially fewer states than the DFA equivalents, represents the solution space we explore with our work. We explore these trade-offs by creating an open-source LTLf to FPGA monitor pipeline. We perform an empirical evaluation to explore the design space and to measure key FPGA performance metrics, including hardware utilization and maximum clock frequency. Our pipeline generates random LTLf formulas for scalability analysis, as shown in the red square. It then goes through the process of generating DFAs and NFAs from the generated formulas, encoding those DFAs and NFAs with truth tables for symbolic encoding, and state-specific hardware for explicit encoding, and finally packing the resulting implementations for targeting an FPGA on Amazon's F1 EC2 instance with the help of the Grapefruit framework. Real-world formal specifications are hard to come by. For this reason, we needed a technique for generating LTLf formulas that we could use for scalability analysis. The first part of our pipeline does this by randomly generating a set of formal specification formulas in LTLf. We provide our tool the size of the formulas we wish to generate, a number of system variables that the formulas are meant to evaluate, and a number of formulas in total. Our tool then randomly chooses patterns from a standard set of LTLf patterns and creates n conjunctions of patterns. We use these formulas in the remainder of the pipeline. The rest of the pipeline converts the randomly generated formulas into FPGA deployable hardware with a series of steps. First, we use Mona, a DFA synthesis program, to generate a minimized DFA from an LTLf formula. The resulting DFA is then implemented with a symbolic and explicit encoding, as shown with the diverging arrows, and finally the resulting hardware is deployed on Amazon's Web Services F1 EC2 instance with Grapefruit. Because Mona generates minimized DFAs, we use a double reversal technique to generate NFAs. For more details on this, see the paper. We varied the parameters of our pipeline to cover automata complexity similar to automata benchmark complexity in previous work, and varied the number of formal specifications from 10 to 10,000. We evaluated the resulting symbolic and explicit automata, as well as DFAs versus NFAs, and found that symbolic NFAs tend to have much lower hardware requirements than the other approaches. We then compare the maximum clock frequency we could achieve on the FPGA and therefore the maximum sampling rate of the monitor among these parameters. We found that NFAs also tended to outperform DFA implementations. Our conclusions based on our analysis are shown in the top right. Our results show that NFAs tend to outperform DFAs, but that explicit NFAs are often able to sample at higher rates than symbolic NFAs, but that symbolic NFAs require less hardware. Our work is implemented in Python and uses the Grapefruit Automata on FPGA tool for targeting AWS F1. Our experiments and tools are available on GitHub. In conclusion, we present a parameterizable open source tool for implementing FPGA-based system runtime monitors from temporal formulas. We use our tool for scalability analysis and explore a contemporary design space that allows us to draw conclusions about the types of automata and automata representations we would choose for runtime monitoring on FPGAs. Our results show that NFAs tend to outperform DFAs for runtime monitoring in both hardware utilization and throughput, and that explicit NFAs tend to run faster than symbolic NFAs. Thank you.